Hi, my name is Jose Luis and welcome to this new video in the series Introduction to Parametric Modeling, where we're going to do a hands-on exercise on generating a facade that is made out of randomly sized panels. And the way it's going to work is that I have this definition. I'm going to create a definition where I have control over the size of a hypothetical facade, and I have control about how many elements are in each one of the horizontal and vertical directions. But I also have control over a certain random variation of sizes that is going to be affecting the panels in each one of the X or the Y directions, as well as having the possibility of play with the seed that is generating this randomness to generate different versions of facades with different distributions, different random angles, not angles, the different random sizes, etc., etc. So with this, now I can create more or less, and this can be an interesting exercise for creating a stone facade, for example, or for creating a facade with panels, and maybe I could even randomly turn on and off certain panels to have like windows and openings. This could be an interesting exercise. This is going to be an interesting exercise to learn how to use randomness, but in a controlled way, in a way that we can explore variation, ranges, and differences, and not just pure absolute randomness. But at the same time, it's going to be a super interesting exercise on data manipulation, because we will actually need to do fairly a few data manipulation procedures like merging streams, flattening data, grafting data. We're going to do a lot of that in this exercise. And I don't think I actually did a great job at explaining that. But if you have watched the previous videos on this series, hopefully you'll know enough to bear with me perhaps speeding a little bit or going a little faster over those topics. So less talking and more doing. Let's go to the whiteboard and let's first think through the problem and do some diagrams before we make before we write any code. Okay? See you there. Okay, as usual, let's do a little bit of sketching to use our brains to think through the problem, and then we can, before we go into actually developing anything. So what we want is, we want to create for example, the facade of a building. And what we want is, in this facade, we want to create it with some kind of pattern that feels random. So what we want to do is, we want to probably have, for example, rows of panels, and each one of those rows is going to have a height that is going to be random. And then within each one of the rows, we would also like to subdivide that into panels in a way that the dimensions of each panel is also in a way random. This could be nice for designing a facade. This could be nice for designing like the layout of some stones for a facade. It could have a lot of applications, right? Now, the problem here is going to be, how do we tame the randomness so that it actually fits the constraints that we have for the facade? Because typically when we have a facade, we have a set amount of parameters. So we know that the facade is a particular height and a particular width, and we have to adapt our randomness to that. And maybe we can also get to choose other parameters, such as, for example, how many of these rows are in the height direction and how many of these panels are on the width direction. So those might be parameters that we're going to use in our definition to control the layout of the random panels. And then the process will probably be something along the lines of first dividing the surface, first dividing the facade into the rows, and then subdividing each one of the rows into each one of the panels. The way we can do that is, for example, we can say, if we know that we have 5 rows, then maybe what I can do is I can just generate a sequence of 5 random numbers and then use those random numbers to drive the size of each one of the rows. The numbers that I just explained here are integers for no particular reason. They could be floats, they could be anything, right? So we're not going to be bound for that. And so let's build this up and let's start with that problem there. And then we're going to see if we run into any problems, and then we're going to go back to the whiteboard to refine this problem. Okay, let's start building this inside of Grasshopper. I have taken the freedom of kickstarting the exercise by dropping in a few sliders for example, the height and the width of the facade. I'm going to be, for the sake of simplicity, I'm just going to assume that the facade is on the ground, or so it's on the XY plane, just to make things a little easier. But it could be vertical. There's nothing really that prevents us from that. And then I've also dropped some integer sliders so that we can control the amount of elements in the height direction and in the width direction. And then just for the sake of visualization, I don't think I'm actually going to need this for anything, but for the sake of visualization, I have placed a rectangle defining the boundary of this facade. This is going to help us during development to understand how things are going. Well, the next thing that I would like to do is, I know that I have 5 rows, so what I need to do is I need to create 5 random numbers, which are going to be the widths or the heights of that random facade. So I'm going to create, for example, 5 random numbers. I'm going to start with 0 to 1, but I'm going to change that very soon. This is going to be 5 numbers, and then the seed is probably going to be, I don't know, some slider that I'm going to call the seed. And for this one, I don't think I will need to, well, maybe I do need to control a little bit the seed. Anyway, and then with this, I have 5 numbers that are going from 0 to 1. And then maybe if I want to perhaps like crank those up, I can just say, well, let me create a slider here and turn these random values from 0 to 10. Okay, and then I get these values here. And then what I would like to do now is I would like to move this plane here a bunch of positions so that I can draw rectangles on each one of those positions. So I'm going to draw rectangles representing the full rows. So for example, what I'm going to do is I'm going to first add a 0 to the list, because remember that I want to always have the same plane. Well, sorry. Now I'm just going to move all these planes here. I'm going to move them in the y direction an amount that is equal to those random numbers. And you can see that I got a list of planes now with all these coordinates. And just because I want to use the first plane as also a row, what I'm going to do is I'm going to merge into this list the original plane. So I'm going to merge to this list that I just created, the original plane, and then I'm going to have the exact same list, but with the first plane on it. And I'm going to, because they have different structures, you see how I'm getting problems here, I'm just going to flatten this so that I get all the planes on the same list. Okay, so now I have a set of planes here, and what I could do is I could use these planes to draw boundary rectangles representing the full row. This is just for us for visualization, okay? So how do I do that? Well, I can use these planes to generate rectangles, okay? And what is the x of the rectangle going to be? It's going to be the width of the facade. So I'm just going to place this in here. And then what is the height of the plane going to be? It's going to be each one of those random numbers, okay? So I get that there. And then you can see that I have now 5 rectangles, but you can see that the last one is duplicated. That is because we have added this extra plane that was the beginning. The beginning, we added this extra plane there. So what we need to do is we need to remove that plane, and I'm going to shift the list here, and I'm going to make sure that this is set to false, and that the list is being shifted in the opposite direction. So -1. Okay, and therefore now I have the same list, but without the last element. So now you can see how I have, for each one of the planes, I have one rectangle marking the full row. And if I do a planar surface, a boundary surface, you can see that this is going to be a little easier to see. Okay? And I think I'm having some overlap issues here. I may need to take a look at that in a second. Let me actually take a look at that right now. Sorry, my bad. I was trying to record this video quickly, and of course that never works. So I forgot that These numbers are the incremental heights of each one of the rows, but those are not the values that I should use for the unit Y direction. Because if I do that, then I'm basically copying the base plane, 1 unit, and then 2 units, and then 3 units, but I should copy them at incremental heights. So that is going to be achieved by using the mass addition, which is going to give me the add the added coordinates of each one of these planes in the y direction. So if I do that, you can see how now each plane stacks on top of each other perfectly, and now things are working well. I actually covered this technique in a previous exercise. I forget which one was that. It was like exercise number, it was the exercise where I was doing the sections of a building and chopping them and laying them flat. So that's where I covered this technique. So you can see that now I have a collection of planes. Each one of these planes is at a height that has been moved by those incremental random numbers, so the heights of each one of the rows. And then I use those to move them and to create rectangular rows that represent rectangles that represent the rows. Okay. All right. Sorry for that confusion. That was my bad. Now, what we have here is that we have a tiny problem. We have two problems first. One problem is that we have decided that the random factor should be somewhere between 0 and 10. Because this is pure randomness, the problem here is that this may randomly give us very large numbers, which is fine, because if we set this to a maximum, that's fine. But it may also give us very small numbers. So you can see how, for example, in this case, we were very unlucky, and then we got a number that was 0.01. So very, very close to 0. And in the real world, we probably don't want to fabricate like a panel that is like tiny, tiny sliver. So we probably want to have a large minimum so that we ensure that there is at least like a body, a corpulent body of material to make these elements with. So I would argue that perhaps we need to say, for example, here we need to move all of this. Let me create some room here for us. Let me move all of this here. And then let's say that if the range is 100, then maybe the minimum range should be a number that is bigger. So for example, let's construct a domain now that is going to go from 5, let's say it starts at 5 and it ends at 10. And that's the domain that we're going to use for the random. Okay? So this way, we are ensure that no panel is going to be like a tiny thing. All right? Now, the other problem that we're running into is that the actual facade is this big. The actual facade is this. But because we are just generating 5 random numbers, there is a very, very strong likelihood that the addition of these 5 random numbers is not going to add up exactly to the size of the facade. So you can see that that can be whatever. And if I actually crank this down, for example, you can see that now the total is like very, very much smaller. No matter how much I play with these two numbers, how much I make them closer or not closer. You could argue like, oh, well, maybe if you play with these numbers, whatever, then I can adjust this to make it almost exactly. But you know me already, that is not a clean parametric approach. So what I would like to do is I would like to find a way to find a rule to take all these numbers and make sure that they add up to the height of the facade. And actually, that is going to be a super, super simple rule. If you think about it numerically, you can say, well, we have the problem that we've generated 5 random numbers. And when we use those random numbers to generate rows, it turns out that those numbers end up being like smaller than the facade. But it turns out that I can actually very easily modify those numbers, because if I know that the total of those numbers is, for example, 27, but I also know how high the facade should be, which is h, for example, let's say it's 50, then I know that those numbers should be roughly double in order to fit the facade entirely and exactly. And I can actually find what the proportion of these numbers should be by saying that those numbers should be amplified by a factor that is equal to the total height of the facade divided by the total height of these random elements that I just got here. Okay? So this whole thing here is the amplification factor that if I multiply each one of the numbers will give me a set of new values that are 1.7, 1.8 times bigger, but it is guaranteed that their sum, all of them together, is going to add up to the height of the facade. Let me show you how that works. That's a very simple numerical rule. So for example, here in mass addition, we know that the second parameter, partial results, give us the incremental additions. But we also have the result, which is the total height. So if we take this result, which is the total addition of all the numbers, and we divide and if we divide the total height of the facade, which is this one, we divide the total height of this facade by the result. Then we're going to get here 1.74, which is the amplification factor. And if we now multiply, if we now multiply that factor by all the random numbers, we're going to get a new list of random numbers that is slightly bigger, but it maintains the proportion. And if I now do mass addition on that one, and I add all the partial results, and I add them all together, you can see that I'm now getting all these rectangles, which are, sorry, I need to plug in this partial, I need to plug in the new sizes, not these ones, but these ones. Yes. So you can see that now I have all these rectangles that are perfectly matching the size of the and now if I modify this, the only thing that I'm modifying is the relative size. I'm actually not modifying the absolute distance. So the actual numbers here, they don't really care. What matters is the actual relation between them, which I think is a really beautiful thing, actually. So, all right. So I think with this, we solved the problem of the rows first. Now it's only a matter of solving the problem of the individual columns for each one of the rows. Now, the problem that we're trying to solve here is going to be the exact same one that we did for vertical. It's just in a horizontal way. And it's going to be for each row, I'm going to need to generate a sequence of random numbers that are going to be whatever. And then I will need to figure out their mass addition, their factor of expansion, and then extend them to cover the whole row of the facade. And that is going to be the same for this one, it's going to be the same for this one, and it's going to be the same for this one, and for each one of the rows. But because I'm not going to do this manually, I want to do this automatically for each one of the rows, I will need to create different random sequences for each one of the rows and make sure that those sequences are different using different seed numbers. So it's going to take up a little bit more of data manipulation than before. So bear with me and let's try to see how this works. Okay, let's go back to Grasshopper. The first thing that I need to do is I'm going to start using numbers, just like straight numbers, because it's easier to explain things. We have right now 5 rows. So what I need to do is I need to create 5 lists of random numbers, each one of them containing 15 random numbers, which is the number of panels in the y direction. So I need 5 lists of 15 random numbers. So how can I do that? Well, should I place the random component and then just copy paste it like 1, 2, 3, 4, 5, 6, 5 times? Is that what I'm going to do? I hope at this point no one is thinking that that's what we're going to do, because that is a really terrible parametric approach, because that basically hard coding the problem, and if I increase this by more or less whatever, I would need to rewrite this part. So that's obviously not a good approach, okay? So you have never thought about that. So I'm going to take, that's not what we're going to do. We're going to take one random component and we're going to say, I need to generate list of 15 values, okay? And as you can see, I actually reorganized a little bit the definition. And what is going to be the domain? We're going to do something very similar. We're going to say that we're going to create another group. We're going to create another domain here. And that's going to be the horizontal variation. So horizontal variation is going to be 2 sliders, the minimum and the maximum, and that's what I'm going to plug in here, okay? And the seed is going to be, for example, is going to be, I don't know, 1,000, okay? If I do that, then the result that I'm going to get is that I'm going to get one list with 15 numbers, okay? Very clean. But this is not what I need. What I need is 5 lists of 15 different numbers. So why am I only getting one list? Because here, as an input, I'm only inputting one domain, I'm only inputting one number of random values, and one seed. So obviously, the result of this is going to be just one list. Now, what I will need to do is one of these inputs is going to have to be a list of data, right? So for example, let's say that, so that when we create this, we get different branches of data. So for example, what I could do is I could create a panel and then hard code, for example, that this panel is going to contain the number 0 and the number 1, 2, 3, and 4, for example, because I have 5, I want to create 5 lists. And I'm going to say that this is going to be multi-line data. And I'm going to plug this here as the seeds. And because I have different seeds, you can see that I now have, for each one of the branches, I have a different list of random numbers, each one of them with a particular distribution of these numbers. However, obviously, this is not parametric, because if I now have like more than 5 rows, this is still 5 numbers, etc., and it's not cool, okay? So we're not doing that. We're going to be a bit more elegant, and what I'm going to say is, instead of doing this, I'm going to create a series of numbers. And the first one could be 0, but so that I have connection with the variability of this, what I can do is I can say the first number is going to be whatever my seed is, which I've already used for the horizontal distribution, whatever my seed is plus 1, because I don't want to use the same seed for 2 random distributions in my panel. So the first one is going to be the value of 1001. Then how many numbers do I need in this series? I need 5, because I need 5 different seeds. No, sorry. This is n is the step size, right? Yeah, so the step size 1 is fine, and then I need 5 different numbers. What this gives me is 5 different seeds from 1001 to 1005, and if I ever change the seed, I will get like a different set of seeds, right? So what I'm going to do that is I'm going to use those as the seeds to my random list generation, and now you can see that my panel has branches, it has 1, 2, 3, 4, and 5 lists, and each one of them containing a different set of random numbers. Okay? Wonderful. So now the only thing that I need to do is I need to follow a very similar process to this one, where I'm going to find the mass additions for each one of these. So I'm basically copying what's going on here. I'm going to find the mass additions, and I'm going to see what those look like. These are the numbers that I'm getting, but these are the partial results. Okay? So the partial results, I'm going to move them. I'm going to use them as x vectors, and then I'm going to move each one of the planes that I got here. I'm going to move each one of those planes. I'm going to move them by each one of these vectors. And as you can see, I am getting data problems because since I have here a list of 5 elements, the first 5 elements of each one goes with the first 5 elements of each one of these. So you see, that is why I don't like flattening things directly from the output. So I'm actually going to do exactly what I always tell everyone not to do, which is what I always tell everyone to do, which is use flattening components, because now I actually don't want this flattened. Okay, correct? So what I want is, I want this data to be grafted. So I want this to be grafted, and I want this graphed here to give me now different planes, you see, for each one of the rows. So now I have 15 planes for the first row, 15 planes for the second row, etc., etc. And you can see that if I change, I just happen to have a distribution that was very close to the size of the thing. So if I now plot rectangles here, on these planes with an x that is going to be equal to, with an x, to the planes, I need to merge the original planes here. So I'm going to need to merge this so that the first plane is plane number 0. Okay? And you saw how the first one was not included. So I need to add the first ones. I need to merge them so that the first one is also included on the list. And now I have 16 rectangles, and I need to shift the list so that the last one is not repeated. So I need to shift that one. I need to shift the list so that the last one is not included. And what I want to do now is, and I'm not doing this correctly because I'm not adding the first one. Yes, so I need to add here to these planes, I need to add, okay, well, I will fix that in a second, okay? But then I'm going to take the X sizes. So those are going to be the ones that I have here. And then the axis are going to be the values that I have here. So those are going to be these ones here. Oh no, and it's not working. What is going on? Well, it looks like I have data problems. So let me try grafting this. So I'm going to unhook this from here and hooking it here. And now it looks good because this should be here and this should be here and this longer one should be here and this one should be here. So I have a problem with data. So what I need to do is I need to add to my original list of planes, I need to add the number 0. So actually, I can probably just add that here. So I'm going to add the number 0, and I'm going to merge this with each one of the branches, and I'm going to plug that in here. And it's not working. Okay, because it's not the same data structure. Yes. Okay, so let me think about this and do it in the right way. Hold on, give me a second. Okay, I found it. The problem was that I was bringing in the collection of planes that didn't have the first one, and those were the ones that I was grafting and bringing into my series. And it turns out that what I actually need to do is I need to bring in all the planes that have just the first ones and not the last one. So those were here after the merging and the shifting. So if I plug that in here, and if I graphed, you can see that now all these planes have the right sizes and they're all matching the row at which they are in. Okay, so yes, whenever you have complicated data problems, don't rush into it because you're always going to mess up. I do it all the time as well. So now that I have this, you can see how I have a distribution of panels in the row, but obviously these panels are not fitting the dimension of the row. Because what I need to do is for each one, I need to do the same process that I did before. For each one of the random distributions of numbers, what I need to do is I need to calculate the total of that row. And what I need to do is I need to, as per the rule that we discussed before, what I need to do is I need to calculate what is the distance of the total row divided by the total distance of panels that we have right now. And that becomes the factor that I need to use to multiply, to amplify this by. So what I'm going to do is I'm going to divide division, I'm going to divide the width of the facade by each one of these total results, and it's going to give me the amplification factor. So now I'm going to multiply each one of these numbers by each one of these amplification factors, and you're going to see that if I had this original list, what I'm going to have now is a tree that has the numbers multiplied by 1 point something, so it's not too much. And then I'm going to calculate the mass addition of each one of these, and I'm going to use the partial results for the translation vector in the x direction. And I'm also going to use those new sizes as the x width of each one of the panels. And as you can see here, now I have the facade that has been subdivided in random panels in each one of the two directions. I'm going to disable all these planes and all this. I'm just going to turn everything off basically. And I'm going to stay with this, okay? And then I'm going to add here rectangles, and I'm going to bring this to the beginning of my definition. Wow, this ended up being quite some spaghetti, huh? Ugh. Okay, so I'm going to leave it up to you, the viewer, to make a better case about ordering these things and making it look clean. Okay, so I'm going to hide this, and this is going to be the output. And then you can see that now, very nicely, we have the rectangles here. We can do planar surfaces if we want. Boundary surface for each one of these. And we can very parametrically amplify the facade in one direction, amplify the facade in the other direction, more elements in one, less elements, more elements. This looks pretty nice, like a stone wall of sorts, right? Less elements, or for example, we can have more elements in this direction, less elements, and if we change the seed, we just get absolutely different random distributions. Similarly, we can play with the vertical variation. If these two numbers are very close together, there's going to be barely any variation, but if they're very far apart, we get a lot of variation. And similarly, here, if there is no variation, look how they almost look like a grid, whereas if we crank up the variation, then there's much more difference between them. Now, I would like to conclude this exercise by reflecting on the fact that what we've done here is an exercise of pure mass customization, because the size of each one of the elements is absolutely random within this control variability that we have generated, but they are random. And each one of the panels in this facade will have a different width and a different height. This typically is very expensive to build, for example, because if we have random panels to choose from, typically we have a particular set of measures that we can choose. Maybe we have like 100 centimeters, 150, 200, 250, and 300. And those are the only panels that we can choose. We cannot choose to have a panel with like 267.5 width, you know? And cutting them would be super expensive. So if we wanted to generate a version of this, where instead of having absolute freedom to choose the dimensions of each element, we wanted to constrain it to a set category of different options, then the technique would be similar, but with a few changes, okay? So I'm not going to cover that right now, but perhaps I may cover that in a future exercise, in a future video, whatever. or in an algorithmic modeling challenging, who knows? But I think this has been a pretty good exercise about working with randomness, but in a way that we can control. So controlling variation, controlling offset, and controlling amount of elements in each direction, and controlling seed values to not be repetitive. So I think with that, I am very happy with where we are. Thank you for sticking around to this video. I hope the whole data part was not overwhelming, and I hope that you could keep up with my back and forths. I'm sorry about that. And thanks a lot. And if you learned something on this video, maybe consider liking it. Maybe you want to subscribe to the channel, and maybe you want to hit notifications to get emails or pop-ups on your phone when we go live or when we publish new videos. In the meantime, thanks a lot, and I will see you on the next videos on this series, hopefully. Bye bye.